Well, I hope I've given you some reasonable perspective on some of the features and issues about food. And what I'd like to conclude with in the next few minutes would be with respect to the molecules of food. They are becoming much, much better understood than they were 100 years ago or even 10 or 15 years ago. The cellular bilayer indicated in this schematic and the activities that go on are many, many. There are transporters of molecules going through the cellular bilayer, the mechanisms for them, linkers of protein materials. The receptors that trigger the little red ball is a molecule that's triggering an action on the other side of the cellular bilayer. And in this case, enzymes are, of course, embedded in the cellular bilayer, and they're changing molecule A or X to molecule Y. And we need these. We need the amino acids that make up these enzymes. We need a good diet that will produce the appropriate amount of enzymatic material, which is, of course, basically our proteins. So it's complicated, and if we were reduced to the size of a molecule, it would be a remarkably complicated landscape that we would be dealing with. So rather than getting into too much detail just for the moment, let's just take a look at a starting point which we need to worry about a little bit, and that's, of course, water. Very simple molecule, H2O. And we'll ask some questions about one very important food that I think many people enjoy, and we certainly, in our promo, we had apples. I was chewing on one and trying to not drizzle it down my chin because they're full of water. What happens when you take a bite out of an apple? There are a number of things in an apple. There are flavors, there's some sugar, there's a considerable amount of water, and of course there's some modest amount of fiber. But if you look at the flavors that amount to what amounts to the flavors in an apple, this is probably a third, maybe even a little more, of the molecules that are in there. Acetone, many of you may know this as nail polish remover. You look down that left-hand column, there's ethanol. There's not enough ethanol to create any kind of physiological effect. There's formaldehyde at the top part of the middle column, that's embalming fluid. And then there's methanol, which is wood alcohol, which in high concentrations can cause blindness. But the concentrations are extremely, extremely small. And then there's 2-propanol, which is rubbing alcohol, and a number of other volatile materials. So we are always consuming chemicals. Many, many of these chemicals, of course, are not harmful whatsoever in the concentrations in which they exist. We're not taking milliliters of them. These are parts per million, that kind of idea. But every time we take a bite of food, we're taking in hundreds and hundreds of chemicals that have a myriad, a very complicated set of interactions one with the other, which makes sorting out what our food process is all about rather difficult. It's even possible to make artificial green apple flavor from molecules that aren't even in apples, but they just happen to taste like apples. So let's take a look at an apple as to give you a chance to mentally guess how many sugar cubes. And this is where you're also going to need to appreciate some of the numbers. Some sugar cubes weigh about 2 grams, some weigh about 3 grams, and others weigh about 4 grams. It just depends on your sugar cubes. So when an article says so many sugar cubes, you want to think about what that is. These sugar cubes, which constitute 3 grams, that's about 18 grams of sugar that's in that particular apple, plus all of those flavors, plus some fiber that's an indefinable structurally, chemically, an indefinable material. But the other one that's in that apple that's very definable is water. So let's see how we would do this. Turns out that's really an easy experiment to carry out. You take a couple of pinpricks in that apple, put it in a vacuum desiccator, take away the air, and the water, of course, comes out of the apple. So we're going to measure this water in terms of a 140 milliliter beaker. So this is partially done. How much water did that amount to? It was around 60 or so milliliters. And if you keep pumping on that, repeat the experiment until you have a constant weight of a core of an apple with all of the water gone and nothing but the fiber and the flavors left. what you have is something that looks like this. It's something like a cork, and the total amount of water in that apple is in fact about that much. So it's significant water consumption when you take in an apple. The question is, what's the percentage by weight? And the answer turns out to be, and you can check this on Google or you can check this in any other source or do your own experiment, which might be kind of fun to do. I did this experiment a while back, a couple of years ago, and it turns out that I happened to get it at the right number. It was the same number. It's about 85%. You might get a little more or a little less depending on the apple. Well, we will be dealing with a few equations in this course. They won't be complicated. This is probably the simplest possible equation, namely the core plus the water obviously yields back the apple. And you might be wondering, what other kinds of foods have water in them? Well, they all have water. And it varies a fair bit. The watermelon, many people think, is the highest concentration of water. It's 96%. Well, we've seen this many times. I've not done the experiment. We've not done the experiment, and maybe we should. But radishes are touted as 98%. It seems a little hard to believe, but that's what the numbers say when you look this up. Well, what I want to do here, just before we start moving into more aspects about food, is just to set the stage for you, something to think about. Because what we're going to do here, I'll set the stage with the macronutrients and the micronutrients. But in between this topic and when we really talk about all of the food materials as to what they are, we're going to have a separate piece of information for the period or for the presentation, which will be how scientific articles are published. This is really important because we hope to give you some aspect and some idea about not only how the articles are published, but what's in those articles, and should we be believing them? How believable are they? And the vast number of journals that are used to deliver the information, not just about food, but about many aspects of all kinds of science. So it's going to be a general discussion about how the process takes place to publish a paper. But right here, I want to just mention some very quick ideas which you can maybe think about and do a few calculations on your own. The macronutrients. The macronutrients are those that you can see: the fat, the protein, the complex carbohydrates, and the sugar. That's the percentage by calorie that is thought to be a reasonable spectrum of percentages for the caloric intake, because it turns out that foods don't have the same caloric value. The grams per day for an average sized person of maybe 60 kilos or a little bit more, and so you can multiply up the number. It's about 400, maybe 440 grams, roughly a pound of food per day, with the complex carbohydrates dominating the gram amounts. It's about a 1 pound of dry food, and we'll talk about this a little bit later. You might enjoy working out those percentages of calories. It's just an arithmetic involvement, and we're going to show you how to do this, and you can figure it out perhaps by yourselves on the way through. Those were the amounts recommended for an average sized person, as I mentioned, but the proteins and carbohydrates have about 4 calories per gram. Fats, there's the problem. It's over twice as many calories, and it turns out that fats are stored more easily in the body than our proteins and carbohydrates. So the body does store all of these materials, but it costs less to store the fats, as it turns out. So it's a double-barreled problem with fat overall. Now, we have left out fiber. Fiber is about 2 calories per gram, but there isn't that much fiber compared to these amounts, so it's often ignored. Those are called the macronutrients. The micronutrients are the vitamins and minerals that we're going to talk about. Vitamins will come up after the presentation about scientific publications, and then the minerals will come up after that, and you will meet Ariel Fenster, who will do the vitamin lecture, the vitamin lectures, because it will be more than one. And there are a great many vitamins and a great many minerals, but they're found in much, much smaller amounts than are the macronutrients. Some are in the gram amounts. That's calcium. That's the only one that hits the 1,000 milligram category. And then it is in the milligram category for iron, and in the microgram category for selenium, amongst others, and we'll be talking all about those. So I look forward to seeing you in the next presentation when I'm going to give a description about scientific articles and how they're published and how we need to know how the science is produced, because we're going to try to support much of what we say by what's in the literature, in the published literature, in the peer-reviewed literature, and that will be the subject next time.